Okay, good morning.
Morning.
Today is March 8th.
Mm.
Yes, March 8th, 2026 is a cosmology discussion group meeting. I want to welcome everybody. I don't see Jim Keene. There's Jim Keene.
Yeah.
Good morning, Jim. Okay,
Hi,
so
good morning. I'm sending a request.
you're going to talk to us this morning about Pauli matrices and binary mechanics.
Yes, sir. Let me share my screen. Okay, can you see my screen, gentlemen?
Yeah, there's nothing on it yet. There we go.
Yeah.
Okay. Well, the news this morning, I guess, is that the Pauli matrices used in the Schrodinger and Dirac time evolution equations, they actually define a cubic lattice, surprise, surprise, in space, in our familiar 3D Euclidean space. The well-known Schrodinger and Dirac time evolution equations in quantum mechanics both require the Pauli spin matrices. And notice that there's a set of three matrices, and each one of the three is associated with a dimension X, Y, or Z of our Euclidean space, which these equations in binary mechanics, according to this mathematics here, actually accept and define. And they, in order to, these matrices are required to produce accurate results for probabilities of real world events. You can't leave these equations out and get the results that quantum mechanics has famously obtained. These Pauli spin matrices reveal the 8 matrices of a cube. In experiments, quantum mechanic equations with the Pauli spinners, is what they're often called, may represent physical dynamics in a three-dimensional Euclidean space. Thus, the Pauli spinners, in fact, define a cubic lattice. In sum, the quantum mechanic equations assume a cubic lattice is a fundamental feature of physical systems. This is what we hope to show today. Consequences of this QM assumption have been explored in binary mechanics, documenting a transition from what I call partial incomplete quantum mechanics to full complete quantum mechanics, aka binary mechanics.
So okay, let me stop you here before you go on.
Sure.
Okay, so I'm not sure I understood this clarifies your notation. I didn't understand your notation in the first paragraph.
For the Pauli spin matrices, they're shown here in figure 1.
Yeah, but your notation confused me. Go back to what does it mean to have those? What does that parenthesis mean? Go back to the top.
Here, this
you got like a parenthesis and then QX, sigma X, sigma Y, sigma Z. What does the parenthesis mean?
Well, the parenthesis
that means anything mathematically, or is that just a
no? It's just telling you, listing. There are 3 Pauli spin matrices.
Okay, I thought that was mathematical notation. All right, proceed.
Well, it is. Sigma X is the first matrix.
But the parentheses don't mean anything. It's English meaning.
It's a group. It's a grouping.
Okay, all right. Well,
it's a parenthetical insertion into the sentence.
Okay.
It's just English.
It wasn't clear to me. I thought that was mathematical notation.
No, it's English.
Okay.
English language notation. Okay, here we go. Here are our Pauli spin matrices, and you could call them 1, 2, or 3, or just the one associated with X, the one
Well, there's
associated.
your parenthesis again. That's what confused me.
Well, this is mathematical notation here.
Okay.
Parentheses are commonly used to define a matrix.
That's why I was confused in the beginning.
All right. Well, hopefully, is that confusion clarified now?
Yeah, but I would suggest you remove the parentheses and just use commas.
Okay. Using the full, so let's give some background now of how we're going to use these Pauli spin matrices. Using the full quantization postulates of binary mechanics, energy was quantized at a new microscopic level, and spatial structures were defined as shown in figure 2, which is probably somewhat familiar to folks here. I've shown it before, where we actually break down the complex amplitude and parse out parts of it. For example, rather than just saying IY, we can where I is the imaginary number, square root of -1. Rather than saying IY, we can divide Y into two parts. Its sign, plus or minus, and its absolute value in the same way for X here. And so we get this, we can sort of derive these spatial structures starting with the spot unit combined in 3 dimensions to make with 3 spot units to make what I call a spot, and then the spot cube, which has 8 variations of the spot. This is all just background here. So let's get through the background. 2 types of energy, M and L, are located in adjacent elementary volumes called spot units, represented as 1 states named quanta, and 0 state M or L loci are empty. So that if these loci are empty, they're in the 0 state. M equals 0, L equals 0. If either one or both contains something, we call it a 1 state, and it's a quanta of energy because we're quantizing energy in this in this theory by limiting the absolute values of X and Y to 0 or 1.
If I may be just a little pedantic again, following Harry's point, do you mean sign here or signum? Because SGN is a symbol for signum, which is not quite the same as sign, plus or minus. It varies between -1, 0, or +1, depending on the value of X. So
right.
in other words, is that the signum?
Sign Y, good point, Ian, thank you. SGN or sign Y can only equal plus or minus. There's not 3 alternatives there.
Okay. Well, one might say SIGN then, just to avoid it being possibly confused with signum. Anyway.
Right. Okay. Oftentimes in computer programming and so forth, the SIGN is shown as SGN, and that's a valid point. And thanks for the clarification. Okay, so we've got 2 kinds of energy located in adjacent elementary volumes called spot units. And the spot unit loci are size L cubes, where L is the quantized length unit in the Keene scale. 3 spot units may be assembled along the axis of an absolute reference frame, space X with orthonormal axes X, Y, and Z, to form a spot. Finally, 8 spots form the spot cube spatial object based upon the 8 possible permutations itemized in figure 3, which is from table 1 in the previous publication. The bit function, which is equation 2 in binary mechanics postulates, replaces the quantum mechanic wave function psi. That's PSI, psi. Okay, the spot cube content. Let's take a look at this. To make things simple, we have in figure 3 here, spot cube content in 3 different formats. In other words, top, middle, and bottom. The symbols are at the top, where we can just assign a symbol, an arrow going to the left for minus L, or to the right for plus L. The same way with minus fractional electric charge for minus M, and plus fractional electric charge, which is 1/3 the elementary charge, for plus M here. So that in the top, we're just going to look at the content of the 8 columns here and 3 rows, each row corresponding to a dimension X, Y, and Z in our space. In the middle, we have signed pairs, which is a lot simpler. It's just another way to look at exactly the same thing as what we have up here. There's nothing new. The bottom one is the bit function in the complex format. And here we have signed complex numbers indicating the values of the spot units in each of the 8 elementary particles. These 8 columns map to 8 elementary particles defined in binary mechanics. So let's see, we have the top, the signed pairs, middle, and complex at the bottom. Each column represents 3 spot units aligned to the X, Y, or Z axes in a spot. IJK is spot coordinate position in a spot cube. For example, 0, 0, 0 is actually a coordinate within the spot cube, 0, 0, 0. We just leave out the commas above here in order to fit everything into this table well. Okay, in a lattice of spot cubes, IJK represent modulo 2 parities. In other words, is the coordinate in XYZ space even or odd? That's what modulo 2 parities mean. If it's even, I or J or K is equal to 0. If it's odd, I, J, or K is going to equal 1. That's what modulo 2 parities are in math. And these are the parities of the integer spot coordinates X, Y, and Z in our space. In sum, excuse me, in sum, the spot cube consists of 24 spot units, 3 rows times 8 columns. Now let's look at the Pauli spin matrices. As presented previously, and this was way back in 2010, this was the first paper in binary mechanics, so that these equations are found there with slightly different symbols, but they're found in the original paper back in 2010. 3 pairs of equations establish that the Pauli matrices define a cubic structure in space. This is the point, I allege, that current practitioners of quantum mechanics are not aware of, although they've been looking at these Pauli matrices for many, many decades, maybe 50 or more years. Actually, it's probably more like 70 or 80 years. First, the sigma X matrix inverts JI parity in spatial dimensions I, where I equals X, Y, or Z. And here are the formulas, a pair of formulas. What we're going to do is take one of the elements in the table I showed you above for the bit function in its complex format and pre-multiply it by a Pauli spin matrix, namely the X matrix. And you see that if the parity is 1, it becomes 0 in equation 1. Conversely, in equation 2, if the parity, position parity in this Euclidean space is 0, it becomes 1. So we're swapping zeros and 1. In equations 1 and 2, the sigma x converts subscript j from 1 to 0 or from 0 to 1 respectively. Okay, that's our big story here. Second, what about the y matrix, the sub y matrix? This inverts ki parity in spantal dimensions I. Here we have the same thing as in equations 1 or 2, except, excuse me, a little cough there. We're going to pre-multiply this time by the Pauli matrix sub y, and we're noting that the last position subscript k is converted to 1 from 1 to 0 if it were 1, or if it started out being 0, it's converted to a 1. And so there we have again in equations 3 and 4, sigma sub y converts k subscript from 1 to 0 or from 0 to 1 respectively. Finally, whoops, what did I do? Let's see. I clicked on the wrong thing. Okay, third, the sub z Pauli matrix inverts I parity along any spot unit axis I in space S. Okay, so here we're going to pre-multiply the complex format for a spot unit where the I parity is 1 and the sigma sub z converts it to 0 and vice versa in equation 6. In equations 5 and 6, sigma sub z converts subscript subscript I from 1 to 0 or from 0 to 1 respectively. So let's talk about this. We call it in science a discussion. So let's see, what did I do? Okay, let's go back down here to, since each Pauli matrix is associated with one of 3 spantal dimensions, x, y, and z, equations 1 to 6 establish that the Pauli matrices define the 8 vertices of a cubic spantal object. Each Pauli matrix, in other words, the basic idea of binary mechanics has always been there in the equations of quantum mechanics. It's just that the practitioners of quantum mechanics didn't know it. Well, now they're going to know it because I'm reading from a published paper published a few weeks ago, which basically is presenting what was presented exactly in 2010. Each Pauli matrix defines a 0, 1 position swap. The position swaps in equations 1 to 6 occur when the complex representation C of a spot unit is pre-multiplied by a Pauli matrix, as shown in equations 1 through 6. In effect, these equations change focus from one spot to another, the columns in figure 3 above. There may be substantial scientific significance of this fact, since the 8 spots map to 8 elementary particles in figure 2. Thus, while the electron may be the key player in many experiments, there may also be participation of other elementary particles in the observed effects. Is this the most significant role of the Pauli matrices in the Schrödinger and Dirac time evolution equations? Question for you all. The present analysis suggests that other particles may participate in production of experimental results which have been historically presented as the behavior of the electron, and just the electron and no other elementary particles. This is the punchline. Pauli spin matrices, again with our parentheses, we're just listing the 3 of them here, okay? Reminding you of what their symbols are 3 complex Hermitian and unitary matrices. The Pauli matrices are often used in quantum mechanics literature to represent the spin minus 1/2 operators. In addition, in this article, the Pauli matrices were found to specify a cubic spatial structure. As discussed previously, the Pauli spin matrix set in the Schrodinger and Dirac equations have produced excellent results, say for electron behavior. The quantum mechanics people, just go bonkers saying to how many digits of accuracy the Schrodinger or Dirac equations can produce in describing observed electron behavior, what they're calling electron behavior in these experiments. Physics literature presents a variety of somewhat cryptic explanations of why use of these matrices works to produce results as predicted. I'm saying here basically that the use of these matrices is required because there is a cubic lattice in space. In outdated quantum mechanics literature, the time development equations may wrongly portray complex interactions among the 8 binary mechanics elementary particles represented in the spot cube as the behavior of a single particle type, such as the electron, whereas in fact, there may be complex interactions which are completely opaque to the present advocates of quantum mechanics because they're unaware of the cubic structure of space, which appears to be required for their own equations to work to provide what the exact results with many digits of accuracy that they obtain and that they attribute to, say, the electron alone. If this is true, the bottom line is that quantum mechanics is simply unable to represent correctly events at the binary mechanic level of microscopic fineness. This possible quantum mechanic fail is a major limitation for continued usage of quantum mechanic formalism in both scientific and commercial applications. In contrast, binary mechanic formalism, the equations 1 through 17 in reference 1, provides an unprecedented means to achieve substantially greater accuracy and resolution in physics experiments and in commercial design and engineering tasks. So that, my friends, is basically the presentation. I might point out, if I can manage to do this, oh, it's covered up above. I wanted to change the page, but they have all this Zoom symbols up here. So I don't know whether, oh, there, they just disappeared. Let me see if I, oh, okay. This page here shows a new site I have at jamesjkeene.com, which gives a nice tutorial on binary mechanics. And this page, which I can now click on, shows you the Pauli equation and how the spinors are used in quantum mechanics. And I wanted to point out as a sort of an addendum to my talk today that this equation uses unexplained constants. These, like mass for particle mass, let's say the electron rest mass, electric charge Q is in these equations. Here's Q, and here are Pauli matrices here, and as a vector. And here's the mass of the particle here, so that what they're doing is using, oh, they're putting them in parentheses again. My God, what are they doing? That's terrible. At any rate, what the point I'm making here, this is from Wikipedia, that they're using unexplained values for which are called fundamental constants, wrongly, according to binary mechanics, in their equation. So they're way behind binary mechanics, because we have at Binary Mechanics Lab actually derived from first principles these values for electron mass, elementary charge Q, and so forth. Okay, I guess I should stop there. I just wanted to point out that they're using these. By the way, related to cosmology, in very low, actually particle mass is not even a constant. They're calling it a constant. At very low energy densities in a simulation, the mass goes way down. And for example, one might think of interstellar space, or intergalactic space, even more sparse in terms of its energy density. And yet they might be still using the mass of the proton, some 1,836 times the rest mass of the electron, as its mass. But in a low energy environment, such as in intergalactic space, the mass of the proton is a small fraction of that mass, according to binary mechanics, which throws all their cosmology equations off in terms of using mass in what they conceive of as the gravity effect and so forth. So let me stop there and see how we've done, and proceed. Thank you.
I think that might relate to Halton Arp and his intrinsic redshift.
I'd like to hear a presentation on that.
Next week.
Mm-hmm. Thank you, Rick.
Okay, so we have an advertisement for the discussion coming up next week. Okay, thank you, Jim. I have a whole bunch of questions and I'm not really sure where to start, but maybe other people have questions. Can you go back to the presentation?
Yep, here we are.
Okay, there are a lot of things that pop out at me. Yeah, okay. Go up further. Yeah, this is a little problematic for me, but keep going. Oh, stop. Okay. Now you talk about the quantum mechanic wave function psi. And that, to me, the first question that came up in my mind, does that mean that you say the bit function B replaces the quantum mechanics wave function?
Yes.
Do you mean that more or less symbolically, or do you mean that physically? I mean, the psi function, as I understand it, is a probability. Well, it's the psi squared is the expectation probability of a particle being in a place. But is that what you mean there, or do you mean something
Yes,
different?
well, the advantage of the bit function is that not only does it represent particle position, it also represents the momentum of the particle, whereas psi is generally thought to represent only one or the other. That's a vast defect in the quantum mechanic wave function, so that's really obsolete. Why would you even use it if you had the bit function, which represents both position and momentum simultaneously in one little package?
Okay, but my question is the bit function an expectation value or a probability, or is it
No, it's the actual locations of the quanta, the one states.
okay, so here's the point I'm trying to get at. Your bit function is a deterministic thing, if you might use that language. It's not a statistical um, object, if you will.
Correct. You could use that language.
Okay. So the bit function in you don't deal with the Heisenberg uncertainty that says we can't really know where a particle is located, that sort of thing.
Well, that's what I call the dumb universe theory. The Heisenberg uncertainty principle, which we might call the Heisenberg ignorance principle, actually, I call it the dumb universe because the physicists thought that they were very smart, but the reason why there seemed to be this uncertainty is because the universe itself is dumb and not the physicists. So that what we have with actually the application of the so-called Heisenberg uncertainty principle is really measurement error that's possible in terms of random variations when we gather a sample of data. So it doesn't really tell us anything about the universe as a whole or how the universe actually even works. What it does is just is referring to observer uncertainty in terms of getting valid measurements and reliable measurements.
Okay. So your theory is so you're saying when you talk about this table and spot cubes and you're saying that these are actual places where the particle is and how it moves. They're not statistical averages or anything like that.
Exactly. Where the energy quanta or one states are, just to clarify there, if I may. And for example, if each of the three fractional charges at coordinate 1, 1, 1 in the spot cube, if each of these fractional charges is minus, then we have the electron, because that adds up to the charge of the associated particle at that location being -1. The same way over here, we've got the positron. And you notice the handedness is determined by the arrows going to the right or the left. And of course, these arrows are just symbols to represent plus or minus L in terms of its directionality. So that the product of these minus signs shown down here is going to give you a left-handed particle for the electron and a right-handed particle for the positron.
Okay, well, this leads me to say, which I'm sure you don't want to hear me to say. It would be nice if you had like a chart that kind of identified these symbols that you have in the figure 3 with electrons. So you say 1, 1, 1, that's an electron, right? 0, 0, 0, that's a positron. That's my understanding of what you just said. Is that correct?
Exactly. And that's shown in this figure here, where here are the coordinates of the particles. This would be the electron 1, 1, 1, right here. And if we look at the other side, oh boy, it's going to cover up. The zoom covers up so I can't jump there. There, I got you. Okay, if we look at the other side of the cube, here's the positron at 0, 0, 0. So these items are represented and in fact actually named. Like the matter particles are the electron, which is in the yellow, and the 3 down quarks, dark red, green, and blue, shown here, 1, 2, and 3. And the lighter red and green and blue are your so-called antimatter quarks. Now, some people I know don't like to use the term antimatter, and you could just call them the other side of the cube, if you will. You can give them any name you want, because I'd like to remind you, we have the math for all of this written down in equations 1 through 17, so that you can call these anything you want. These are just words that are often used in physics literature, so I tried to make it easy for people to absorb the material.
Okay, thank you for that. I find this kind of it's like you've condensed things, uh, but I'm not really comprehending what's going on yet.
Well,
Yeah, yeah.
what's
You
going
understand
on?
what I'm saying is that it's kind of hard for me to sort of visualize, what you're talking about. I mean, these diagrams are helpful, but I have a hard time sort of understanding what it is that you're getting at. Anyway, that's my comment.
Point well taken. So I'm trying to do my best, and but the best that I'm able to do may not be good enough, and so I invite others here and elsewhere that may see this video in the future to write a little book on binary mechanics and explain it better than I can explain it. Now, the equivalent I just might throw in here of the Dirac or Schrodinger equations is equation 17 in the paper Binary Mechanics Postulates. And in that paper, equation 17 just shows the bit function being modified by a sequence of 4 bit operations, which are the quantized version of operators in that we use the term operators in classical or conventional quantum mechanics. So that equation 17 shows you a bit function at time 0. You operate on it with these 4 bit operations in a certain order, and you get the new state of the universe, which is the bit function at t equals 4, because it's assumed that each operation occurs in one quantized time unit. So that equation 17 is the binary mechanics version of the Schrodinger equation.
Okay, but you don't have quite that equation 17 here. I'm not sure what it looks like. We're
Right.
running out of
I
time
don't
here.
have that up for display. Well, let's see. Do I have that?
Okay, we're running out of time here. Okay, go
Okay.
ahead and do that.
Well, I could display the paper that has that equation,
Why
and
don't we do
perhaps
that
if
when we come back?
okay, great. I'd be happy to do that.
Um,
It's a little difficult for me to shift from one tab to another tab in my window here, because sometimes Zoom covers up the tabs, so I can't click on them. But when we come back, I'll have the other paper with the binary mechanics version of the Schrodinger equation, which is very simple. In other words, it's not difficult to understand how our universe works, actually.
You can minimize zoom quickly and maximize it to find your stuff, James, easily.
Oh, okay. All right. So where do I minimize it? Well, it looks like we got
Top
39.
top right.
Top right.
It's the little beside the X, there's a box, and then there's a minimize beside that, a little dash.
For some reason, that's off the screen. I don't see at the top anything there.
Huh. Okay, never mind.
Anyway, I'll have that page displayed when I get back. If I go here to posts and scroll down.
all right, welcome back. Um, I guess what I was wondering, Jim, is there seems to be a kind of a parallel formalism between what you're doing and the official version, which is referred to as quantum mechanics. And it's not, you referred to the psi function, and your Pauli matrices seem to operate on the bit function. It's not real clear to me, or you're doing matrix operation on the Pauli matrix are operating on the bit function, which in your notation is bold BC. Is that correct?
Right, yes.
Okay.
The complex representation of the bit function, which for those who like complex numbers, which most people don't, but it's there for those. A lot of people just love complex numbers. Now I've got the postulates paper, and I'll go down to equation 17. It's down here somewhere. 14, we're getting close. 15, 16. Hello, we're 17. 16. Good grief. There it is. Okay, equation 17. At first I thought, my God, it's not in the paper. Something happened. Oh, okay. So here we have the binary mechanics version of the Schrodinger equation. We're going to have our bit function at time equals 0. We're going to operate on it with three.
Okay. Wait a minute. Let me understand what what the notation is. You're using parentheses. Does that mean they're matrices or vectors? I'm not really sure.
Well, the bit function is a
Well, you
is
have
a
it
listing
be,
of the states of any number of spots.
so that would be a vector.
It
Are
would be
these
a
not
vector.
functions of functions? Is that what we're saying?
Yeah, you could view it as a three-dimensional matrix. Yes, I guess you could. At any rate, it's a listing of the states of any number of spots. For a single spot, there are 6 possible, there are 6 states or 6 loci. And so therefore, 2 to the 6 different variations are possible, or configurations. So here we're going to have our bit function for any number of spots at time equals 0. Where all these parentheses indicate the order of application of the operators. This is our scalar bit operation S. The unconditional bit operation is then applied. And then the vector bit operation is then applied. And F stands for the strong bit operation. And when all 4 of those operations have been applied, we have one cycle of the universe completed, and we now have a new bit function at time equals 4, because we're assuming that each one of these operators, S, U, V, F, applied in that order, gives us the new state of the universe at time equals 4, that each one of these takes one tick of time to apply. So
Now
that
these operators is S. So as I understand it, B is a vector in a kind of a binary space. Is that correct?
a vector in a binary space.
Yeah, but well, a vector in which the components of the vector are ones and zeros.
Okay, well, here's the scalar bit operation right here. It is 2 adjacent bits in the one state and an empty destination. Okay, so that that is when that configuration occurs, we have what's called a scalar force, and it could equal 0 or 1. If this logical expression evaluates to 1, then we have the scalar force is applicable. If not, there's nothing happens down in our equation 17. So I hope, you know, all of this talk about vectors and this, that, and the other, we're dealing with binary logic here. It's that simple.
Yeah, but I don't understand how the operators are, what it is what objects they're operating on.
They're operating
But what
on,
do you mean by operator? And that's kind of what, I'm not really sure what this, in this equation 17, I'm not sure what the symbols, what the symbols represent. I mean, in one case you have a B, which I'm assuming is some kind of a state, according to what you've told me. It's
yes,
it represents a state, a physical state. And then S is doing something to it.
right.
As
If
an
S is
operator.
true, if S is true, then the M bits are moved from the M loci to the L loci. That's what this operation does, as explained in detail in the paper. So that we're talking about binary logic equations here. You could say that this is a vector or that's a vector, but really, I think anything could be, any collection of numbers could be called a vector. So that yes, the bit function at time equals 0 is a collection of numbers, and yes, I guess you could call that a vector if you so desired. No objection.
Well, that's my understanding of what you mean. Okay, what you just said, that's my
Well, I
understanding.
mean a collection of numbers which are 1 or 0.
Where the position in the collection denotes a property, or what you would say a bit location, right? So what
Right.
is like,
Well,
okay,
in the spot unit, which is the basic foundational item in this spatial structure that we're talking about in binary mechanics, the there are 2 types of energy, M and L. And that's where we get the fact that there are 2 types of energy.
okay. So then I guess my issue is about the 17. So I'm not sure, by parenthesis you mean some kind of operational, the parenthesis indicates that you have a bit function and then S does something to the BT, and then the next time, then the U does something to the result of S
Exactly.
acting on BT, and the
Exactly.
V.
Yes. So what Harry just said is exactly what this equation is saying. In other words, there's a certain order where, in fact, my research has shown that if you change this order from SUVF to some other order, you get different results. Therefore, I have concluded that there's only possibly one bit operations order, SUVF, which is actually correct. I mean, I'm assuming we've got one universe here, okay? So that if you're getting different results from different orders, it must be that the only one of those possible results is the correct one. And so that the bit operation order is everything. And in fact, in our discussion of Nobel Prizes, if anyone can, this order here is what I believe to be the correct one. However, there's still more work required to actually pin that down. In other words, that is still a sort of an open question. And if anyone can establish that this is the one and only correct order that is possible, that matches actual data and experimental results, I mean, that's worth about 3 or 4 Nobel Prizes, together.
Okay. Um, So now, if we go back, this equation 17 is sort of replaces the quantum mechanics formalism as far as um, these where they have an operator acting a Hamiltonian operator operating on a state vector.
Exactly. This is the new quantum mechanics, which is complete and full instead of incomplete and only partial. You notice
Okay.
that in none of these results that I've reported in various papers, in none of these results are the so-called fundamental constants, which are unexplained measurements, in my opinion, at least prior to binary mechanics, they were unexplained, are used. So that if you have to depend upon unexplained measurements like the speed of light, electron, elementary charge, and so forth, you're way behind the game. And as I showed in the last session, from the Wikipedia entry, they're still back in the Stone Age in conventional quantum mechanics, relying upon these measurements, which in fact can be shown to be gravely flawed. For example, the mass of a particle, even its rest mass, depends on quantum density. And so that all of the calculations in terms of energy density based upon, let's say, proton mass for all the hydrogen out there very sparsely in intergalactic space are way off, perhaps by several orders of magnitude, according to binary mechanics. So there's just a whole lot of disappointment that you get if you are not interested in pursuing the full quantization postulates of binary mechanics. You're just really, in a way, operating in the dark, in my opinion.
Are you saying that a proton can be different sizes in different areas of space?
No, different observed masses. Remember,
Okay.
from Newton's second law, the mass depends upon the how much the particle is accelerated with a given force.
Okay.
Yeah. Okay. Now, I noticed that Ido isn't here. He sent me a copy of his book. I think he sent one to Ian as well. I don't
Yeah.
know uh, whether any other participants got copies of it. And it was really long. And I guess my interest would go to your table. I'm going to ask you to, but I think you have a reproduction of your table. It seems to me like we passed it. The table 3 from your presentation previously that you were talking about earlier. The table
Right.
3, I think
Well,
it was.
in this paper, we have that table
Okay, let's
complete.
talk about that table. Okay, that's
See,
it there.
here's the full table. I only
All right,
today.
okay, all right, hold on.
Yeah.
Now, the issue is that comes up for me, and this is an issue that's been discussed in the dissident community. Is there a neutrino in this table?
Yes. All these zero states are neutrino components.
Well, that's not, is the neutrino a particle or not in your theory? Maybe I should put it that way.
Well, there's a whole family of neutrinos, according to particle physicists in the conventional literature. I've gone so far as to to state that if a locus has a zero state, that's a component of a neutrino.
All right, now you kind of got me on that. I don't really get it. Kind of went over my head, I'm afraid.
Well, we've been talking about loci
Okay, so
having
let me
one
ask
state.
let me ask this question. You've got 0, 0, 0, 0, 0, 1. All you've got 8 locations in your eight um 8 combinations of 3. I think that's what that is.
Yep.
8 um
Ugh.
and 0, 0, 0 you said before represents 0, 0, 0 represents a positron, you said.
Yes, and that's shown at the bottom right here, if you can see it. A right-handed electron, and it's with the plus charge. That's the symbol I'm using for it. It's a lepton, and the name for it is positron. Let's see if I click one down. Yeah, there you can see the positron.
Yeah. I think I commented on this before that I would prefer the particle names to be at the top rather than at the bottom, but that's okay. I um, didn't notice that earlier. So where's the neutrino in this table? I don't see it. That's
Well,
my question.
whenever you have a zero state, if L or M is 0, that's a neutrino. See, L and M can equal 0 or 1. When either one equals 0, that's what I'm calling a neutrino component, or a 1-bit neutrino, if you will. I couch it in those terms because conventionally physicists recognize a family of neutrinos of different sorts and compositions. So I'm just saying, well, our zero states the neutrinos are built from zero states for the L or M loci.
Yeah, but I don't
What
even
about the
see.
neutron itself? Do you conceive of the neutron as not fundamental, as Ito does, for example, that it's composed of a proton and electron?
Okay, well, the proton cycle um, does not include either a positron or an electron in that cycle within a spot cube. Okay, so that if you add an electron in what would otherwise be a just a proton object, then you have a neutron. And in my view, these electron spots can move around among different nucleons within a nucleus with multiple nucleons, such as deuterium or lithium or carbon or any in the periodic table. In other words, which proton may have an electron residing in its home spot cube can change over time. It's not necessarily fixed, as some people think, that, well, this proton is always really a neutron because it contains an electron. Well, what if that electron moves around among the proton particles within a nucleus, so that I'm leaving that open? In other words, I'm not just saying forever and ever within a multi-Z nucleus that a particular proton is always a neutron if there's an electron there, because the electron itself could move around among the proton particles. And well, so which one is the neutron and which one is the proton can change over time, as it were.
Actually, I like that idea. I like that description of it, but I guess to really understand it is is not as easy as it You make it sound easy. I'm not really.
Well,
Um,
actually, the good discussion and questions which have come up in today's session and in previous sessions too, I might say, are actually pointing out areas where I try to carefully couch my response in terms of what it says and what it leaves out, because um, I have not even myself necessarily come to a firm conclusion on particular questions that can arise. In other words, binary mechanics at this state now, with over 100 papers published in the Journal of Binary Mechanics, is still in its infancy, even its babyhood, if you will. And there's all sorts of questions which investigators can investigate and to allow then more firm description and conclusions then. So if I sound a little vague, I'm trying to carefully demarcate where binary mechanics seems to specify a route to an answer, but maybe the final answer is yet to be established by perhaps using the binary mechanics simulator or uh, other methods that are experimental data.
okay, so now I'm to try to get down to you don't really you talk about lepton. You've got E plus R lepton, which you identify as positron. You got an E minus L lepton, which is an electron, and then you've got quarks. I don't see any baryons in there.
Right. Well, the baryon or the proton itself would be a composition of actually all of the particle types listed below except the electron. And that's involved in the proton bit cycle. And so the electron is the odd man out. But if an electron occupies its spot in the proton home spot cube, then we would call it a neutron, at least for that moment in time.
Okay, but I guess what I'm trying to get at is your in your way of presenting it, the baryons are composite particles made up of the quarks that you have here in your table. You've
The
got
quarks and
blue,
also
green. I don't see top or bottom in the um,
well, the composition of these well, there are three generations that are generally recognized in the standard model of elementary particles. And the, like, for example, the top quark and the charm quark and so forth and so on are higher generations, which I've shown in the original binary mechanics 2010 paper to be compositions of these particles shown below in this table shown presently.
okay,
So,
that leads to go ahead.
well, so that these three generations of particles, and they even talk about three generations of neutrino to go along with it. And that's why it can get a little bit complicated. But one can view the standard model in two parts. The experimental results, which seem to be rather convincing in defining three generations of particles, and the mathematics, which are a complete no-go zone. I mean, it's just a complete mess. And that's why we need the binary mechanics, so that if you look at the standard model in terms of a collection of experimental results over a number of decades, you're going to find a lot of interesting material. If you look at the mathematics, you're really going off into la la land, because we
Okay.
have a binary universe.
Rick, did you have a comment? I guess I thought Rick was going to say something. Um, okay. So Oh, I know what I was going to say. So I'm going to basically jump out here and sort of say, from your point of view, it sounds like, or my understanding of this table, maybe I'm misunderstanding this table, that in your binary mechanics system, the particles that you have down there at the bottom, which are really represented by these, go up a little bit, we don't see you have positions in the spot cube. Okay, 0, 0, 0, 0, 0, 1. Those define the fundamental particles or the fundamental. I don't know that I want to use the word fundamental particle. It
No,
could be
that's good. Let's use that term, fundamental particles. Binary mechanics is stating basically that there are 8 fundamental particles, and only 8. There's not 9 or 7 or 12 or 14 or any other number than 8. And we have shown, actually, in the very, very first binary mechanics paper in 2010, that all the others listed in the 3 generations of particles, and mesons too, by the way, are compositions of these 8 elementary particles.
okay. So the spot cube defines 8 elementary or fundamental building blocks, if you will.
Exactly.
And the rest of them, so that's what, and the Pauli matrices, to get back to the main topic, the Pauli matrices are what define the vertices of the spot cube, as I understand. Did I say that right?
Yeah. In the very early 2010 paper, the full details of the spot cube were not specified with the degree of exactness as I've done in more recent years, and that is shown at my site, where there's sort of a tutorial of the history of how these ideas developed. But the idea of a proton bit cycle or proton cycle was identified even in the very, very first binary mechanics paper in 2000, published in 2010. It was actually written in 1994.
Okay, now this is kind of, the terminology is new. The proton cycle, is that what you're saying defines the proton as an object of physics?
Exactly. And at my new, I had a lot of this material housed on the angelfire.com site, which has now gone down. At least the free web shell version of it is gone down. And so that's why I went to WordPress and started my jamesjkeene.com, where in the binary mechanics section, you go through the entire history and it's illustrated. And in fact, our own beloved Robert Gray, who most of us know and have interacted with, created a 3D animation of the proton bit cycle, of the proton cycle, and that is there on the website, and you can actually rotate it and look at it from different angles and so forth.
Okay, well, that begs the question, is there a neutron bit cycle?
No, there are only 2 bit cycles, which account for all of the locations in the bit function, and that is the proton cycle and the electron cycle. So there are just 2 of them, 2 cycles.
Okay. All right.
And there are
So that
only
kind of
2.
leads into what Ito is asserting about neutrons being composite entities of protons and electrons.
That would be a similar thought pattern. Yes, I do believe. Ito is quite brilliant. I'm expecting a lot from him in the future.
Yeah, that they're not primary particles, or that neutrons aren't primary that they're a conglomeration of an electron and a proton.
Exactly.
Yeah, I think I'm really persuaded towards this view and have been persuaded towards this view for quite a few years. And of course, the puzzle that's connected with that is the decay of the neutron that produces a proton, an electron, and a neutrino. Did I say that correctly? I think I said that correctly.
Yes.
But the neutrino is the puzzle. It's I don't get the neutrino. That's kind of uh, where
Well,
I
when
sort
an
of
you could think of it this way intuitively, perhaps. When an electron separates from the proton in neutron decay, it's leaving empty locations. In other words, locations or loci in the zero state. Well, those are neutrino components. So it all makes sense within the terminology proposed by binary mechanics, if you will.
okay. Yeah.
By the way, the whole idea in this neutron decay that into a proton, electron, and neutrino, postulating a weak force, that's a complete farce. And my paper, Weak Force Boondoggle, documents that and goes into exactly what we've been talking about in terms of the breakdown of the proton into an electron, positron, excuse me, and electron, proton, and neutrinos. So I might just throw that in, and that has caused all of the weak force Nobel prizes to decay and expire, as we reported upon previously.
Yes, we talked about that last week. I this weak force always puzzled me as to what it is. I still, the strong force as well. That to me is just a big question mark for both of those things.
Well,
Well,
for the weak force, the unconditional bit operation accounts for all of the known phenomena with respect to the weak force.
Oh,
So,
I see. Okay. Well, that's an interesting way of putting it.
and the unconditional bit operation is not itself classified in binary mechanics as a force at all. It's just that for every cycle in equation 17 that we had displayed a while ago, the unconditional bit force, excuse me, the unconditional bit operation is applied, which moves bits away from wherever they were, and in fact, the main effect in, say, an atomic explosion is not related really to a so-called strong force. It's the unconditional bit operation which causes the dramatic explosive effect in, say, atomic and thermonuclear bombs.
in Ito's model, he just uses the Coulomb's force, which is electric. It's the electric force that holds. That is the strong nuclear force, and I think that what they're seeing for a weak force may be magnetism. We know it's weak. It's way weaker than the electric force.
But by the way, the bit operations which are related to forces as defined in binary mechanics, the strong, vector, and scalar operations are called operations, bit operations, because infinitesimal increments are not allowed in binary mechanics. They don't even exist. Everything is binary, and so that you need to replace the infinitesimal operators used in quantum mechanics with the uh, um, finite bit operations, which we saw in equation 17 a few moments ago. That's why we have bit operations instead of operators. You notice the same root, operate, but we have operations in binary mechanics because everything is binary. And we have operators in classical quantum mechanics, which is the fictional version of what we now have in binary mechanics, because there are no infinitesimal operators, in fact.
I think Feynman, by the way, made a similar observation about Coulomb forces being the primary determinant of the energy given off in nuclear reactions, rather than any sort of mass deficit or anything like that. He talks about the Coulomb forces.
Yeah, so I think this is a way of, I think the issue here is that to talk about Coulomb force in the word force, I think is a connection to classical physics. It's I think it's a classical physics concept. It may not really be applicable in binary mechanics as they claim. That is that correct, Jim? Would that be
Well, I'm not claiming that the use of the idea of force, which is basically just a certain configuration of the basic SI units of physics measurement, and we're going to name it a force. That's all, and so I think that still remains a useful idea, or an idea that can have utility. For example, in the Keene law of motion, I actually define an equation for the force due to the motion law using those units of measurement.
Well, the way I see binary mechanics is it's just another form of math that, like the other forms of math, can represent reality and can do a good, maybe binary mechanics does a better job of representing reality than certain other maths can do. And it's, like I say, just math. It's a tool, basically.
Well, I wrote a paper, a good point, Rick. I wrote a paper called Quantum Technology Advances, where the math used in quantum mechanics is going to lead to major errors at a very microscopic scales, at the scale of, say, binary mechanics and the Keene scale, of 2/3 of a femtometer in terms of length, and the other two parameters for energy and time. So that if you're really interested, in other words, if you're interested in a very global, general description of some phenomena, there's nothing wrong, in my mind, with using traditional real number math to describe the phenomena. It's a step in the whole research process.
Well, as we know, computers use on-off binary, and they can represent, or they can generate everything and anything, and reality and non-reality. So I see
all right?
binary
We're coming up
mechanics
to
as
the
just
end
another
here.
tool. Yeah. I just see binary mechanics as another.
Okay, so Rick, we got in your statement there.
Sorry?
I said welcome back. Okay, we I think you got I think you got in your last sentence before
Yeah, I
the,
did. My last word, yeah.
okay. I guess I have some thoughts that I'd like to bring in, maybe, but the topic I want to introduce is um, maybe a bit lengthy, maybe not. Does anybody have any comments or questions? You haven't said anything, Bob. You have we haven't heard from Vladimir, I don't think.
Yeah, I mean, I've run across some of this before. Maybe one question on Pauli matrices. The second one has complex numbers. It sounds, Jim, like you hold a hidden variable theory of quantum mechanics. In other words, probabilities aren't basic. Is that true?
Yes, I'm not sure exactly. I've heard the term hidden variable often, but I'm not sure exactly what you mean by that. But
There are more details that just aren't given with the in the mathematics of standard quantum mechanics.
exactly, well, that I would say yes. In other words, using real number equations such as the Schrodinger equation, um, at
Well, per the time, let's see, dependent Schrodinger equation has a complex number, not the time independent one. But
okay. I guess I'm talking about the one with the complex numbers. But what happens when you use those equations at a finer level, or a more microscopic level, is you can introduce serious errors in the results that you obtain.
yeah, it
And
seems to me that just the way the math is with complex numbers, because you only get a probability even when you have a probability amplitude multiplied by its complex conjugate. Uh, so that makes it very difficult even to have a hidden variable theory because you don't want to describe your hidden variables with something with an I in it. That just sounds like a calculating device. Uh, so it seems, at least the move I'm more attracted to is to try to avoid complex numbers from the beginning.
well, the binary mechanic approach completely removes complex numbers.
Mhm.
In other words, to explain a point in today's talk, I showed you what the complex representation of the bit function is. However, it's not needed in binary mechanics calculations at all. As a matter of fact, in equation 17, which is the basic replacement for the Schrodinger equation, there are no complex numbers in it.
Binary is the simplest math, on off, 1 2 or 1 0 1. I mean, it's the simplest math that you can have.
Well, yes, and if you want to use real-time math, that's okay at a more macroscopic scale. However, the more microscopic you get, the closer to the level of fineness of the Keene scale, which are our three primary constants in binary mechanics, and I've dubbed them the Keene scale, quote unquote. The closer you get to that, the greater the errors you're going to see in equations using real numbers. Okay, so in other words, in principle, if you really want to know what's going on, you're going to be in a load of error if you try to use real number math down to very microscopic scales. You're going to get errors, and big ones. Like, for example, the electron magnetic moment, and a Nobel Prize was given for this, by the way, is more than double the actual rest electron magnetic moment, which is related, of course, to the electron bit cycle that I mentioned. So like, if you want to use real math, you're fine as long as you don't want to get down to microscopic level. Of course, to theoretical physicists, they want to get down to the basic levels. because they want to understand how the universe works. But aside from that, you don't need to go to these microscopic levels for many engineering problems, for a lot of calculations that one might want to do.
Okay, any other comments on that point?
Yeah, but if you truly want to understand the universe, you need to understand how plasma interacts with itself. And those are elementary particles. Plasma is composed of charged particles, electrons, protons, atoms even, and molecules. They all behave in the same way. They all particle and wave.
All
And
right.
that's how a better way to describe the universe at a smaller scale. At that scale, it would be a binary math.
Well, that's what you have in binary mechanics.
All right. I guess I'd like to bring up the Bob already brought up hidden variables. I think you made a good point there, Bob. I want to bring up this business of superposition and collapse of the wave function, and probably I'm going to get a quick answer here. Those notions don't exist in binary mechanics would be my conclusion.
Well, what do you mean by superimposition?
Superposition. Okay. Well,
Superposition.
that's where
Action at a distance.
no. Superposition is this thing that relates to the Schrodinger cat problem where reality doesn't exist until the observer observes it. And all the states are
Right. Okay.
all the possible existences exist prior to the act of observing. And superposition describes all of the states existing prior to observation. That's my understanding of it.
Right.
Maybe incorrect.
Every possibility is possible until you make an observation of that phenomenon.
Correct. That's my understanding. Right.
Yeah, that's really it sounds really psychotic. I mean, this is something for psychologists to deal with. This is more a psychology topic than physics topic.
Well, the idea is that you have a vector of possible states. So all the possible states are described by a vector, and then this quantum operator operates on that vector to produce the result that you measure.
Yeah, and this nonsense brings up multiple universes where each possibility exists in a different universe, and the cat is dead in the box in a different universe. In another universe, the cat isn't even in the box. It's just nonsense, man.
Well, psychiatrists have listened to these sorts of stories for years. You just need to talk to some psychiatrists that have been manning the mental asylums, and these stories are not unusual, or they're quite common hallucinations.
Well, the point I'm
these
asking
are commonly accepted views. So this prompts me to ask my general question, Jim. Many of us who have been looking at the macroscopic properties of the universe and maybe have come to conclusions contrary to those of modern, as they call, settled science, have received a rather unfavorable reaction. We've been called cranks and so on. So I'm just wondering, what, if any, has been the reaction of the main quantum mechanical people to your ideas of binary mechanics? Have you been considered a crank, or have they just left you severely alone?
Well, I'm trying to assess that reaction, so I don't have a final analysis or conclusion specifically, Ian. But I have noticed that the page views for my Journal of Binary Mechanics and for my new website at jamesjkeene.com, no spaces, jamesjkeene.com, to advertise it a little bit, have been increasing. Okay, so that frankly, I don't consider binary mechanics to be in the what's the word, crank category. In fact, I consider binary mechanics to be quite mainstream. In other words, the majority of physicists are not theoretical physicists. They are experimentalists. They are the graduate students doing the research projects, which always are questioning something in existing theory, and that's why they're motivated to do those projects, as well as experimentalists in universities and national labs around the world. So that I consider that binary mechanics is one major player in this scene, and not as anything that you might call fringe or uh, dissident at all. In fact, I regularly quote these investigators and the results to support the conclusions of binary mechanics. So, I don't consider myself a dissident at all. For most physicists, the minority of physicists who pride that, who characterize themselves as theoretical physicists, well, yes, they're sort of in their own la la land, as Harry has pointed out, with the kind of hallucinations that he described a moment ago. But the majority of physicists are right in line, and I quote them. As a matter of fact, I think these sessions and the Saturday sessions as well should concentrate on new papers in physics review and physics letters and elsewhere of new research going on. In other words, we should talk more about what's actually going on in physics, and not, what a few theoretical physicists say that are really haven't been institutionalized, and they're still running around with their delusions.
And they call us woo woo.
Right.
Okay,
So in other words, that's why a few weeks ago, Rick, your excellent presentation, I critiqued it for like branding. You want to brand certain things as the electric universe and so forth. Why not brand yourself and this work as astrophysics, as physics, rather than some rubric term like Thunderbolt Project or whatever? And just consider yourself part of the physics community worldwide, as opposed to some subgroup which is ostracized mainly because of the way it has branded itself. Binary mechanics hopes to brand itself as what physicists are actually doing in the experimental world of investigating of how things work. That's what physics is as a science, how things work.
Right. I get you. And them calling the electric universe is just a descriptor of the electric charge that's moving through the universe, powering everything.
In other words, astrophysics.
Yeah.
Why not just call it astrophysics?
Well, because mainstream calls it astrophysics. Their astrophysics is different than our astrophysics.
it's a branding issue. Okay, got it.
Well, around the world, everybody's physics is a little different from everybody else's. That's the normal situation, Rick. That's not something unusual.
Yeah,
okay?
I understand that. I understand that fully.
Every PhD project, every research project that's going on around the world today is based upon one or more investigators involved in that project attempting to shed further light on what physics really is, okay, and what is verifiable and what's not verifiable.
Yeah, but they're all working within
what your work as something other than physics or other than astrophysics may be have unfortunate results because you sort of are labeling yourself as an outcast or whatever.
Well, with the addition of universe to electric, kind of implies that it's describing how the universe runs. But
Okay,
anyways, I get you.
go with your brand. I mean, each has to choose their own path, and I respect that.
But the mainstream, they will not accept electric currents flowing around everywhere, powering everything, initializing Z pinches, which then, as Ito was conjecturing, the activity of fusion is the power source, Harry, that you're looking for.
Well, the further that you go, Rick, the more sort of off the track you might find yourself. For example, you started by saying physicists don't recognize electric currents. Well, I'm sorry, they do.
Not in space, they don't. And they've only started doing that in about the last 10 to 15 years. There's only
Well,
a very few papers about electric current in space.
What you want to do is publish results from space demonstrating these currents.
Yeah, but we don't have
astrophysics.
But we don't have probes out into the intergalactic Birkeland currents, the space in between galaxies. We just
so
don't
that
have.
You're actually asserting that this is just a theory, is a supposition, and there's no data to support it.
They're looking.
There
is data to support it.
Then that data should be presented and call it astrophysics.
The fact
Okay.
that. Okay. Never
That's
mind.
my suggestion. Anyway.
Yeah, I get it, but yeah.
All right. Okay, so I guess we sort of close that topic. So we got dead silence here. Jim, you sort of made a lot of comments in your response to would you I'm going to broach this subject. This is, favorite subject. When you talked about hallucinations and all this other stuff, it seems to me that relativity is sort of Einstein and his relativity is sort of the main culprit here of what you could call insane people that should be in an insane asylum. And I mean, if you look at some of these videos on YouTube explaining, I've been looking at Bell's spaceship paradox. That one's a fun one. I mean, it's just crazy physics. Then there's the pole and barn paradox, and it's actually advertised as crazy physics. There's the Asylum channel where he says, he comes in, oh, here, crazies here today. We're going to talk about this crazy stuff in physics that you crazies will appreciate. And I find that branding rather puzzling. Have you seen this channel, Jim?
Oh yeah, well,
I think it's the Physics Asylum.
I'm not sure about
right?
that channel because I would skip over that, but certainly on YouTube, you have a lot of videos, which I think the main objective of these videos is to spread confusion, and and I can't necessarily criticize that, because the more confusion that is spread, the less likely it is that physicists in other countries that might be at odds with the sphere of influence of the United States might get some insights. And the last thing we want is for physicists in other countries to get insights. And so what we want to do is to spread as much confusion, like we had the whole flat earth craze and other kinds of ridiculous notions that on YouTube. So that's my take. My take is that it's actually a campaign to cause confusion.
Oh, okay, that's um, but I think the issue boils down to what is physics. Um,
How things
and
work.
now you sort of say that how things work. That's kind of very simplistic, I think. Um, um,
As it
I
should
don't
be.
think I don't think they're doing. I don't think physicists or the physics. I don't think they're doing how things work. I think they're doing how we want to claim things work and fit the world into their viewpoint, their philosophical orientation, if you will.
Well,
You
are
seem to
you
have
perhaps?
made a distinction, Jim, between theoretical physicists and experimental. And I think, if I'm not taking it wrongly, that you've attributed most of this nonsense to the theoreticians. But I think the experimentalists have a lot to answer for as well. And I think in particular that if one tried to register for a PhD or something in experimental physics in one of the major international institutions and said that your starting point was that you thought um, superposition and the collapse of the wave function to be psychotic, I think you'd be given a short shrift.
Well, I don't think any serious graduate student would frame the research in that way to begin with. In other words, if we were to talk about real people, real graduate students in major universities, Caltech, MIT, Harvard, so forth, Princeton, you're going to find serious people, and their projects are invariably designed to test some feature or some claim of theoretical physics to hopefully shed by their work more light on that topic. And that is what you're going to find physics students today, and also those who are now on faculties and so forth, or staff of national labs doing.
Oh,
And they don't frame it in the sort of shall, if you don't mind, the incendiary way that you expressed it. And I
well,
understand your point. It's a good point. But
the
I would claim that uh, the majority of these research projects are actually designed to test aspects of existing theory in physics, but they're presented in a way that is consistent with that scientific method of pursuing truth.
I would say that the two types of physicists aren't exclusive. They're they're experimentalists that come up with theories. So, and then there are true theoretical physicists that just think, just sit there and think based on other people's experiments. So,
Yeah, I agree with what Rick said. I might point out something from my own experience. I wrote to the authors of this paper showing zero electron dipole moment, which is a prediction of binary mechanics, that the electric dipole moment of the electron is zero. And there were groups both at Harvard, excuse me, both in the US and in England working on this, competing with each other to get their measurements closer to zero and with more sigmas of accuracy, to show that in fact the electron electric dipole moment is zero as predicted and stated by binary mechanics. So I wrote to one of these investigators an email, and what their response was, I wrote asking why he chose a sphere for the electron shape, in agreement with his data. And he just said in his reply, and by the way, if we want to spread what we're doing, write to investigators and don't talk about your own work, talk about what they're doing. and ask them questions about what they're doing. I guarantee you're going to get a response. At any rate, the response I got was basically the shape consistent with a zero electric dipole moment was a sphere. And I pointed out in some of my papers as a result that a spinning top, which is the shape of the electron according to binary mechanics, also has a zero electric dipole moment. So you see, this experimental physicist of some great notoriety, they're publishing papers going back and forth between the US lab and the other group in England or Great Britain, and they just take from the theoretical physicists, well, if the EDM is zero, then it must be the shape of the electron must be a sphere. So they just accepted what the theoreticians were saying, not being theoreticians themselves. But they could have said, well, the electron shape could be a sphere or a spinning top because both have zero EDM, but they didn't. But anyway, that's a little story from my own experience that if you contact researchers about their work, asking questions to get insight into what's really going on, you're very likely to get a response. And this whole thing about being, we're dissidents and there's them and then there's us, which I think are artificial distinctions. All of us want to find the best ideas which are going to be more productive in increasing understanding. End of speech.
Agreed.
Well, I think your point is,
Again,
I think the point is that that's, you look at these videos where they talk about this crazy physics, that doesn't seem to be moving us towards the objective which you've enunciated, understanding how things work.
Well, I agree. And my theory, which is only a theory, is that this is done intentionally to cause confusion.
All right, yeah, you
That
said
YouTube's part of YouTube's mission with respect to physics and science in general is to cause as much confusion as possible. Perhaps some people in powerful positions think that if the population is confused, they're more easily controlled or whatever. I'm not going to even enter into theories about that. But I think it's generally social engineering.
Well,
Well,
the military was gathering information about people, and once Facebook started, they stopped their programs because all the information that they were gathering was coming in through Facebook. They just started using Facebook's data for their information gathering.
okay. Any other comments?
Sorry, that's a little bit conspiracy theory, but that's the truth. That's what happened.
I'm more to the point of view about YouTube is that it's about people wanting to get views and collect as much money as they can, and I think it's marketing to a certain extent.
Well, I mean, yes, it is marketing to a certain extent, but YouTube is part of that company that is Meta now. So,
oh,
I
I
mean,
see. I see
it's
what you're
all
trying to say.
it's all like James was saying, flat Earth.
I thought YouTube
ET.
was part of
Well,
Google.
he didn't say ET. No, Google is owned by Meta.
No.
Google is
Google
owned
is
by Meta since when?
no.
Google's
Google is
owned by
owned by
Facebook.
Alphabet. Like, okay, I see. Google is not the same. YouTube is owned by Google, which is not Meta. Pretty sure.
Agreed.
Although it's very confusing sometimes because Meta changed its name and used to be Facebook. And when I see Meta It, I don't think Facebook anymore. I think they did do that deliberately. That was marketing. Uh, uh, I think the issue that the dissonant issue that you're commenting on started with John Chappell and his group, which goes back to the relativity issue, which to a large extent, the dissident movement is really an objection to the physics, which promotes absolute certainty. Einstein's theory is correct. And they also are promoting quantum mechanics is absolutely correct. I would say that you're a dissident in promoting binary mechanics, because binary mechanics is saying pretty flatly, as I understand it, that all of the claims or the conclusions or the postulates and the fundamental beliefs that surround quantum mechanics are false. Not correct? I mean,
Well, like each person can make their own analysis, and I have no objection to that. So that,
so
if you want
you're
to
not
say that,
taking a position on whether quantum mechanics is false or not, but you've made statements that you pretty much say these people are crazy for asserting certain conclusions from
that's true.
it. I see binary mechanics is based on completely different principles, and and I questioned about this. I mean, you're not dealing with the Heisenberg uncertainty. You're not dealing with statistical probabilities, and you're not dealing with reality is created by the collapse of the wave function at the moment of measurement.
Exactly. In other words, we start with binary mechanics with the three axioms or postulates of quantization, which I call full quantization of space, time, and energy. And those are radically different postulates than anything you find in any other physics theory, whether it's general or special relativity, or really any other that I'm aware of. So yes, binary mechanics is a departure, and it could be called a dissident event, if you will. But yeah, so that's my take on that.
Well, in addition to that, you are asserting that there's a different set of what we would call fundamental particles. You've got 8 particles. None of the only
Well, it's not a different set. The 8 particles are all included in the standard model first generation list. And so that they're not 8.
Yeah, they're included as a subset, but they're not a complete set. Your fundamental particles are a subset of what, I'm not even sure what they claim a fundamental particle is in their theory. So I'm not clear about that.
Well,
You don't have proton as an example, and you don't have any baryons as I pointed out.
those are all of the elementary particles, the 8 that I defined, are within the standard model chart that you normally see everywhere. All the others beyond those 8 are compositions of those 8 as shown in the original 2010 paper published, and in other papers where I've extracted that information and presented it in separate papers, showing that all of those particles are compositions of
All
the
right.
original 8.
What about the Higgs thingy? Do you have any comments, or is the Higgs thingy in your binary mechanics?
Yes, I have 2 papers on the Higgs boson and field, and I view those as a primitive attempt to describe the strong force as defined in binary mechanics. They're quite primitive attempts. but they do show the equation for the field, for example, shows two components, which are complex numbers, which map to spot units, adjacent spot units in a spot in binary mechanics. So they're sort of close, but the defect, again, is that at this level in binary mechanics of microscopic examination of things, their real number treatment of the Higgs field and boson is rather primitive, but it was sort of on the right track, actually. And I describe that in two papers. Just go to the journal and on the right column, just scroll down to Higgs and click on that, and you'll get straight to those two papers.
Okay, any other comments? We're coming up to the end here. We haven't heard from you, Vladimir. Do you have you're just being silent, or?
Not expert in this business, I cannot understand anything. I'm very sorry. I'm so classical that for me, all the quantum physics outside of my mind.
Okay, well, I
I'm very
appreciate
sorry.
your listening.
Many times I told about Jim and his theory that he can talk about some quantum physics and so on. But to translate all this knowledge to cosmology, to the whole world, I don't know how to do it. That's why, as a part of quantum physics is fine. As for the classical physics, I have totally different approach to the notion even of classical physics. The classical physics dealing with ensemble of quantum objects. If he will collect his different particles, different ensembles, and then he will show some new features, new properties, new characteristics, new numbers, I will be more than happy to see them and to apply them to the whole world. Simple like this.
Okay, we're coming up. We got 2 minutes. Jim, I want to thank you for talking, giving a talk and starting the conversation going. And I appreciate that. Do you want to make some summary comments?
Well, I just am very appreciative to Sir Harry Richter for his great questions and providing a forum for my little presentation. And I might note that Vladimir just talked about ensembles of quantum objects, so that you see, I think Vladimir has an open mind that there are quantum objects, and I hope that maybe binary mechanics might help in terms of defining what those objects are. Thank you.
Okay, I do have one comment that I wanted to make that I didn't make, and that is perhaps it might be useful to you to attach links to your website to videos in which you've given these presentations, and that might be helpful. I don't know, but you might want to consider that. That would provide these conversations to people who might be interested in learning more about quantum mechanics. I mean, binary
Good
mechanics.
idea. That gives me the platform to announce my new website, jamesjkeene.com. If you go there, you'll get a history of the development of binary mechanics.
Yeah, Roger Anderton, he posts all these videos on his YouTube site, so you can point them right there, James.
Thanks, Rick.
All right, thanks everybody. I think we got a minute here. So Rick is going to talk about Halton Arp next Sunday, I believe. Is that correct?
Yeah.
And that should be interesting. And
it's just a general talk about it.
All
Doesn't
right,
go
and I
deep
guess,
into it.
and after that, we don't have anybody